640,000 years ago, Yellowstone ejected 240 cubic miles of ash in a single eruption. Now, satellites have confirmed what scientists hoped would not return. An 18-mile-wide bulge on the North Caldera rim is inflating again. With over 200 earthquakes in just 4 months, the Norris Anomaly is back. But the real danger beneath this park may not be what you think. Yellowstone's reputation as a supervolcano is built on numbers that defy imagination. The Lava Creek eruption, 640,000 years ago, expelled nearly 240 cubic miles of ash, enough to bury entire cities beneath a layer dozens of feet deep. This eruption carved out the present-day caldera and left ashfall traces from California to the Gulf of Mexico. The sheer scale of that event has fueled a persistent fear that Yellowstone is a ticking time bomb capable of ending life as we know it across North America. Yet the ground above this ancient magma system is not silent. Over the past century, scientists have tracked countless small earthquakes, shifting geysers, and subtle changes in the land itself. The Norris Uplift Anomaly, an 18-mile-wide bulge on the caldera's north rim, has become a key focus for both researchers and the public. Its movements are measured in centimeters, but the questions they raise are immense. Is this the first whisper of another super eruption, or simply a sign of Yellowstone's restless nature? The numbers set a daunting benchmark. The Uplift episode from 1996 to 2004 raised the ground beneath Norris by nearly 5 inches, a change that covered an area the size of Chicago. In 2025, satellites and GPS arrays detected the anomaly swelling again, though this time the rise measured just over half an inch. Still, the memory of that ancient eruption lingers, shaping every new tremor and every fresh data point into a source of speculation and concern. The story of the Norris Anomaly is not just about what could go wrong on a catastrophic scale. It is about how scientists use the largest eruption in Yellowstone's history as a yardstick, measuring today's subtle changes against the shadow of an event that redefined the continent. As the ground shifts once more, the search for answers turns from broad fear to the specifics of what is happening beneath Norris right now. On the north rim of Yellowstone's caldera, the Norris Uplift Anomaly has become a touchstone for understanding the park's underground restlessness. Its story is written in repeated episodes of inflation and subsidence that stretch back decades, each tracked with growing precision as monitoring technology advanced. From 1996 to 2004, the ground here rose nearly 12 centimeters, almost 5 inches, across an area 18 miles wide. At the time, this was the largest uplift ever recorded in Yellowstone, and it was first detected not by the naked eye, but by satellite radar and early GPS stations that caught the slow, steady rise beneath Norris Geyser Basin. Scientists traced the cause to magma accumulating around 9 miles below the surface, a depth confirmed by later modeling and still referenced in official United States Geological Survey assessments. After 2004, the uplift slowed, then reversed, with the land subsiding a few centimeters over the next decade. But the anomaly's reputation for unpredictability was cemented in 2013 when a sudden pulse of rapid inflation, much faster than the earlier episode, was abruptly halted by a magnitude 4.9 earthquake. That event, centered directly beneath the anomaly, released built-up pressure and sent a sharp signal through both seismic and geodetic networks. The pattern was clear. Uplift at Norris could accelerate without warning, and sometimes it stopped just as quickly, often in response to seismic events rather than volcanic eruptions. These cycles of rise and fall have made the Norris Uplift Anomaly a prime focus for the Yellowstone Volcano Observatory, a partnership led by the United States Geological Survey and university scientists. Today, the observatory's director, Michael Poland, sums up the lesson with a simple observation: the one constant is change. His team relies on a network of GPS receivers, satellite interferometry, and real-time seismic data to watch every subtle movement. The anomaly's track record, marked by decades of measured inflation, sudden earthquake-triggered drops, and no eruptions, has shaped how geologists interpret new signals. When the ground began to lift again in 2025, it was not an isolated event, but the latest chapter in a story that has played out again and again on Yellowstone's restless rim. Satellites orbiting hundreds of miles above Yellowstone delivered the first unmistakable sign, a subtle circular bulge spreading across the Norris Geyser Basin. In July 2025, continuous GPS stations P711 near Madison Junction and NRWY just south of Norris began recording a slow but steady vertical climb. By December, the ground had risen about 1.5 centimeters, covering an area nearly 18 miles wide. This uplift, though modest compared to the 5-inch surge from 1996 to 2004, stood out against a decade of relative calm. The most compelling evidence came from Sentinel-1 interferometric radar, which mapped the surface deformation in detail. The resulting interferogram displayed a classic bullseye pattern, concentric rings of uplift radiating from a central point beneath the basin. This signature, spanning from October 2024 to October 2025, confirmed that the ground was not just shifting but rising in a focused, measurable way. The pattern matched closely with earlier episodes, linking the current anomaly to the same restless source deep below the caldera's rim. Horizontal GPS measurements revealed another layer of movement. Stations positioned on opposite sides of the anomaly drifted apart, tracking the outward push as the ground swelled upward. The data stream was unambiguous. The Norris Uplift Anomaly had reawakened, and the motion was not random. It was systematic, centered, and persistent, beginning abruptly in July and continuing through the end of the year. These precise, overlapping measurements left little doubt. The ground was on the move again, echoing the behavior seen in past inflation episodes. But the scale and tempo were different this time, less dramatic, yet impossible to ignore. With the anomaly confirmed, attention turned to the seismic record, searching for the next piece of the puzzle beneath Yellowstone's surface. Beneath the swelling ground of the Norris Uplift Anomaly, the crust responded with a surge of micro-earthquakes. Between September and December 2025, the Yellowstone Volcano Observatory cataloged more than 200 seismic events clustered within a 10-kilometer radius of the uplift center. The daily quake rate, usually just a handful, spiked sharply in November, with over 100 events in that month alone. Most of these earthquakes were small, with magnitudes less than 2, but on November 17th, the strongest reached magnitude 2.7. This was not a random scattering. The quakes lined up at depths between 8 and 12 kilometers, mirroring the vertical push detected by GPS and satellite radar. Such swarms are not new to Yellowstone, but the timing and location drew immediate scientific scrutiny. In past episodes, like the 2013 rapid uplift, seismic bursts coincided with sudden changes in ground motion, sometimes even halting inflation altogether, as with the magnitude 4.9 event that year. In 2025, the earthquake cluster began after months of measured uplift, suggesting that the crust was responding to accumulating pressure from below. Each tremor relieved a fraction of that stress, like tiny cracks adjusting in a slowly expanding shell. The pattern told a clear story. The ground was not simply rising, it was straining, flexing, and occasionally breaking under forces deep within the caldera. But the energy released by these quakes remained modest. No large faults slipped, no surface ruptures appeared. Instead, the swarm acted as a mechanical pressure valve, releasing tension before it could build to catastrophic levels. For scientists, these events were crucial data points, evidence that the deformation was real and that the system was active but not eruptive. The next step was to look deeper, using geophysical imaging to trace the source of both the uplift and the seismic unrest. Magnetotelluric imaging, led by researchers from the University of Utah and the United States Geological Survey, has provided the clearest picture yet of what lies beneath the Norris Uplift Anomaly. Their models reveal a zone of high electrical conductivity centered 12 to 15 kilometers below the surface, deep within the crust, far beneath the shallow hydrothermal features that dot the basin above. This conductive region is interpreted as a crystalline magma mush, with only a few % of the rock present as actual melt. The numbers are precise but sobering, less than 5% molten, the rest locked in a solid, high-viscosity matrix. The estimated depth of this zone, around 14 kilometers, comes with a margin of error of plus or minus 2 kilometers, reflecting the limits of even the most advanced imaging tools. As one magnetotelluric researcher explains, the uplift is not a sign of a liquid magma surge racing toward the surface, but rather the slow pressurization of a partially molten reservoir, an underground system that is restless but not eruptive. These findings set the stage for a careful checklist. What would truly distinguish routine unrest from the first signs of a coming eruption? Yellowstone's eruption warning checklist is built on decades of monitoring and hard-won experience. The USGS and Yellowstone Volcano Observatory track 4 main indicators: ground uplift, earthquake activity, volcanic gas emissions, and thermal changes at the surface. A true eruption precursor would show a rapid, sustained ground rise, more than 5 centimeters in a matter of weeks or months, paired with a dramatic spike in shallow earthquakes, a surge in sulfur dioxide gas, and rising temperatures at geyser basins. In 2025, the Norris Uplift Anomaly produced only about 1.5 centimeters of uplift across 18 miles, well below the alert threshold. Earthquake rates increased, but most events were small and deep. Gas and temperature readings stayed at background levels. As Michael Pollan puts it, the one constant is change. The data reveal a restless system, but not one on the verge of eruption. For now, Yellowstone's greatest dangers remain the hazards that arrive with little warning: hydrothermal explosions and strong earthquakes, not a catastrophic volcanic blast. Beneath Yellowstone's forests, the magma chamber, mostly crystalline and not molten, reminds us that danger here rarely arrives as an apocalyptic eruption. Instead, it is earthquakes and hydrothermal blasts we must watch for. If this was interesting, subscribe to Violent Planet and let us know what topic we should cover next. See you in the next video.